And welcome everyone. Thank you all who are listening. Welcome to the last and final workshop on therm and window components. I mean, it's only the second one. It's only part two, but we're going to be we're going to be. This is actually also it's both the last of the therm and window series, and it's going to be kind of the last of a lot of the environmental design webinars that we're going to do in this session. We got two more coming up after this that are just going to be on software development. So thank you everyone for coming to this one and for the opportunity to do this series. But all right, let's dive right into it. So all right, so last time, for those of you who stuck around, were around here, we did some therm modeling of opaque constructions. Of some wall constructions in particular, that I'll review that a little bit briefly, where we calculated the R values of different construction details. And in this session, we're going to be also using therm again to look at construction details. But we're going to be looking specifically at windows and integrating glazing systems from windows and modeling the frames in therm, the frames of those windows, and all their detailed little components that, especially in aluminum frames, exist. And then finally, we're actually going to both start and end the workshop by integrating the results from therm models into an Energy Plus simulation. So that we can get actual values of energy use and not just sort of R values or U values at the end of everything. Or comfort. Energy or comfort are both things that we'll get out of this. So just to situate, I mean, to run you through the schedule that we're going to have today. So we're going to start, as I said, by integrating, working with Energy Plus and integrating the last session's results. So specifically taking, making the design decisions based on the results that we got from those therm models, and building an Energy Plus model so we can actually tell what the energy use is or what the comfort is for the design case. Next, we're gonna import a window glazing system, do some frame modeling. So each one of these is going to be 30 minutes. We're going to improve. We're going to try an alternate window frame. Just in the same way that we tested a few different examples last time. That's going to be 30 minutes. And then finally, we're going to integrate those windows into Energy Plus based on using the LB&L window software to help us do that a little bit. All right, and so just so that you know, the parts of the whole sort of honeybee insect that we're working with today, we're going to, again, just like last time, we're predominantly working with therm and window, the connection between honeybee and these two LB&L power tools. Well, power tools in the sense of that they're very powerful, not actually like drills and hammers and stuff. And then we're going to be looking at the link between integrating with Energy Plus, as I said. So again, we've already had about 4 sessions where we've done work with the Open Studio Energy Plus connection. And so I'm not going to try and get too deep into that because there are other resources available on that. There are also a lot of free YouTube series on that. But we're going to be focusing a lot on how these two work together. And just as a refresher from last time, in case any of you had missed it, and just so that you know where we're picking up this time. We had modeled the kind of wall construction system that was had insulation in between steel studs, as you kind of see this work we're doing here. And so we had found, though, when we had tried to account for the heat flow that happens through these very thin but also very conductive steel studs in the wall, that it was degrading the R value or the resistance of that construction by almost half. In our case, and so I mean, this was just to sort of illustrate the point that these thermal bridges in our constructions make a huge difference. And while we were able to show that, we were able to build this a therm model, a finite element heat model of this. What we're going to do now is that, well, I guess first I should say again. I mean, this is exactly how, if you were to take a thermal image of a house, you'd see all this heat flow happening through those studs. In comparison to everything else, but what we're going to do this time, we have to ask, what does this mean for our energy use and comfort? Because R value, it's not necessarily real value that's quantifiable in terms of energy use or in terms of comfortable hours. That it's a step removed, I guess, from the things that we count as really valuable in our buildings. And so in order to do that, we have to deal with this, again, which I sort of covered very briefly in the introduction last time, but is now going to be very relevant for what we're doing today. This distinction between steady state versus dynamic simulations. So when we built these therm models last time, we were just looking at a single kind of point in time, and not even just a very special point in time where we've had constant conditions on the inside and outside for, assuming for a long enough period of time for everything to become stable. And so that's what we mean by steady state. That we only had one temperature on the inside, one temperature on the outside, and we just, want to look at, if that's the case, what does the heat flow look like through the construction? But in reality, I mean, this never really happens that you just have one temperature on the outside and one temperature on the inside, one temperature on the outside that's constant. And just over the course of the day, things are going to change dramatically. You're going to get all sorts of different heat patterns, actually within this construction. And so we really need to we need something, not just something that allows us to model our construction details in a high resolution spatially, but something that allows us to capture this dynamic capability. Especially this is really critical because we're not really going to get a good sense of energy use, annual energy use, or annual comfort from this because it's a point in time. So we need something dynamic in order to actually reach these more valuable metrics, that we have. And so that's where, we've used therm to model this steady state heat flow, and we're going to use Energy Plus to do this type of dynamic calculation this time. And just, a lot of you probably already are very familiar with Energy Plus and whole building energy simulation, but just so that you guys are aware, I'm just going to give a very, very brief background of exactly what we're doing with Energy Plus and Honeybee today, a little bit of what's under the hood. This is just saying exactly what I said before. Our value isn't necessarily valuable. You really have to run it through an energy simulation to understand what exactly is the value that's delivered at the end of the day. And we're using Honeybee to bring these two together, sort of. So Honeybee as you guys saw in the diagrams in the intro, it's an interface for both of these things, and so it allows us to kind of more easily bring the results from therm, put them into Energy Plus, and get out measures of value. And just so you know, again, that the energy modeling software that we're using, the way that it's doing this dynamic calculation, because I've kind of explained roughly what steady state is, the dynamic calculation is just doing, this is a slide from the previous time, it's doing a calculation of the energy that goes into the building has to equal the energy that leaves the building. So that's the first law of thermodynamics. Energy is never created or destroyed. And what Energy Plus, it just runs that calculation every single 15 minutes of the year. And that's what allows us to get a very dynamic picture of how our building works over the whole year. And again, just so that you guys are aware, kind of just a brief history of what's under the hood. Just before, because we're only going to take a very surface level view of Energy Plus in this part here. But really, Energy Plus, I should point out, it's an engine. So it's an engine just like some of you guys are, still most of the industry models a lot of stuff in an engine called Do2 and an interface called eQuest for that, which was developed back in the 1980s and then kind of by 1995 was kind of set and became the industry standard. And this is what most of the industry still uses today. But starting in 1995, we have Energy Plus, which is the engine that we're using. That's been in development, I guess, now for, that makes it, wow, that's almost 30 years. So it's been a long time to, is that right? Yeah, no, 20 years. And now, as of 2000, in around, I think, 2008, Open Studio became this kind of interface. It's still very much so under development, interface for Energy Plus, and that's what we're going to be plugging into today. That's directly what Honeybee is talking to. And therm is also somewhere very close to here to the present. First Window came about, and then therm came about, and they're both, both within the kind of Open Studio era in some of the more recent time period here. So we're really working. This is just to show you that that the stuff we're working with today is kind of at least in terms of the longer timeline at the cutting edge. All right. So with that, let's dive right into the example because most of today is really going to be a software intensive day for those of you looking to understand what are the capabilities built in right now. All right, and so I'm going to go back to, Arpin has sent you guys a Rhino file. And the Grasshopper files that we're going to be building today. And again, just so that you guys remember what we had worked with, we're kind of building a treehouse, mostly because I've chosen it because it's a nice small scale where, you know, we can, construction details are really one of the major design elements. The other reason why I've chosen it is because it's, you know, it's got a lot of surface area to volume. So really the whole ability of this small structure to perform is really dependent upon the envelope more than almost anything else. And the other thing is that, I mean, finally a third reason is that it's you know, it's my fantasy to live in a treehouse, and my ambitious fantasy is to live in a treehouse, probably, you know, or at least have a treehouse that's occupiable for the vast majority of the year. And so we're gonna at least try and model this at first in Energy Plus to see, are we actually going to be able to stay in something this small all the way into the winter if I really don't put in an official heating system. Like, how cold is it going to get? Is it really going to be like winter camping, or you know, or what's going to be the situation? So, in order to find this out, I'm going to open up Grasshopper, and we're just going to, you know, which a lot of you, if you guys don't have it open, you just type Grasshopper, and we're going to we're going to start by just building a single zone small energy model of this treehouse. And in order to do that, let's see. So it's going to be relatively quick. This is going to be a lot of review. For those of you who had stuck around for the energy modeling stuff, this is going to be a lot of review. But like all of our definitions, we're going to start by dragging and dropping ladybug onto the canvas, and then we're going to drop honeybee, because that's where all the libraries that the other components reference are in there. And then what we're going to do, we're going to bring in our zone geometry. So we just need a closed volume representing our zone. And I'm just going to bring up an empty geometry parameter here. And let's see. And you'll see I've actually, so you'll notice that this actual geometry that's displaying right now isn't completely closed. It's got holes punched for the windows and doors. But you'll see I've given you guys as an Energy Plus layer that has that closed volume on it. You know, it's all one surface. And this is what Energy Plus really needs, because it needs to understand that it's only one volume. And actually, sorry, I turned off the windows, but I really meant to turn off the zone. There we go. All right, so we've got one closed volume here. Let's bring that into Grasshopper. All right, we're just going to set one geometry. All right, and the first thing that we need to do, because in Rhino this is only just, you know, it's just geometry. That's the only information associated with it. But we know that energy models require a lot more things in order to actually run them, other than just geometry. We need schedules. We need a program, we need constructions and wall constructions and everything. So I'm going to drag and drop the Honeybee masses to zones on the canvas, which is under the 0 tab, and this allows us to take any kind of closed volume like this and converts it into a zone with all those properties auto-assigned, basically. You'll see that we have one other required input, which is a Boolean here to create the zones. So I'm going to connect the Boolean toggle, double-click, connect the Boolean toggle, double-click to set it to true. And then we've created those HB zones. And you'll see that we get out of this in the same way that we put in a B-rep or boundary representation, or, you know, Rhino's way of saying a closed polysurface. You know, we put in one B-rep, we get out a B-rep, but we know from the previous examples that there are a bunch of other properties being assigned here. And maybe we'll just take a second to check what some of those default ones are. I'm going to use the Honeybee label zones component. And I'm going to connect up some zone attributes here, also under the 0 tab, just so that we can see what's being assigned here. And I'll set this to wireframes so you can actually see. And I'll turn the preview off on that geometry. So we see the zone there. It's calling it, you know, labeling it zone 0, which sounds appropriate. And we can see that the default zone program, let's say if we connect that up to attribute, is an open office, which this is most certainly is not. Yeah, treehouse is probably pretty far from an open office. So first thing that I'm going to do is I'm going to change that zone program to be something more residential, because I'm thinking, like, you know, I'm living here for a long period of time. So I'm going to use, there's a list of Honeybee building programs under the 5 tab. I'm going to grab that. and we're going to take residential schedule just probably from the mid-rise apartment template here, and I'm going to connect up list zone programs. So we have a building program, which is this, which we connect to the zone program component, and then we see that we have 3 different types of mid-rise apartment programs. We have the apartment itself, the office, and a corridor. And I'm definitely modeling an apartment here, so I mean definitely more the living space than other parts. So I'm going to take a list item component, and I'm just going to connect that up there, and you'll see that'll select out by default the first item in this whole list, so that I just get the apartment there, that native grasshopper list item, and then that's what I'm going to connect to zone programs here on the zones input, on the HB zones, master zones component. All right, and so let's move this over a little bit, make some space. And so now you see, now it's got the zone program that's being assigned to it is for apartment. So it's going to automatically have all the loads and schedules and everything are going to be for this residential kind of apartment template, which I think is decent enough representation for what we have here. The other thing that I'm going to check here is what are some of the other attributes? Let's see, is it conditioned? And so, all right, so you see by default it's making the zone conditioned. And I've already told you guys that, I'm not really thinking of putting a heating system in here. So, I mean, or at least for the purpose of the simulation, I want to model it without a heating system. Maybe we find that at the end of it, we can model it, have a heating system that's just a hairdryer or something. But yeah, I'm gonna set is conditioned to false here. And so now you see, now it's no longer, it's going to be exported without anything to kind of control the temperature in there. So we're just going to be looking at the raw passive nature of this treehouse. And then finally, I think that's really all that I need to assign here. I mean, there are a bunch of other things that you guys you can check out here, but this is really the most important. I think this is a decent enough representation of at least of what my treehouse is. The only thing that maybe, something we're going to change is we're going to change the default constructions because by default it's using very generic exterior walls that are just kind of an average of the insulation over all the climate zones of the U.S. So we're definitely we're going to change that to be our therm construction. But let's see. All right, so we've got our zones. We need to add in our windows next, right? Because this is just a closed volume. And so in order to do that, I'm going to use the Honeybee add HB glazing component. I'm going to pass the zones through this component and along with the child surfaces, which are the window surfaces, just another way of saying window surfaces, and that's going to add the windows to the zone. So I have to first bring the windows into Grasshopper here. So I'm going to select the 4 windows of this treehouse. All right. And I'm going to make another empty geometry parameter, and we're going to go set multiple geometries. And all right, so now we see those surfaces are in Grasshopper. Those are going to get connected to child surfaces there. And so now we're going to, if I turn the preview off on everything here, actually maybe I'll even hide the geometry here. You see now that zone has the windows assigned to it. This, what's coming out of here. All right, and so again, those are just generic window constructions that are being used of a double pane, I think, without any low E. So, all right, but let's say, all right, we've got this, this is at least a rough representation before we start to take into account our therm constructions. Rough representation of the treehouse. There's really just one other thing that I need to do, maybe to make sure that, this is a decent representative of a passive building, and that's allow the simulation to open the windows if it gets too hot. I mean, we're really going to be simulating it in the cold time of the year, so I'm not really too concerned about this. But I think it's it's just good practice if I'm modeling a passive building to include some natural ventilation. And so under the 8 tab here, there's a component that allows you to set the airflow of a zone. Again, just like this other window component, you connect the zones to this, and you get zones out of this that have natural ventilation assigned to them. And I'm just going to set some default values here. I've already gone through these in other sessions, so I'm going to do this very quickly. I'm going to do window-based natural ventilation, which is that one option there. There are a few other ones like fan-driven ventilation available. And I'm going to say anytime the indoor temperature goes above 22 Celsius, then we should naturally ventilate. But maybe I'll also say if the outdoor temperature is below 12 Celsius, it's not a good time to. It's just going to be too cold. You're going to get drafts and everything. So all right, so only these conditions we naturally ventilate, and then maybe I'll say, because I don't really have too much cross ventilation, I think here. I mean, yeah, I'm going to play it safe. I'm just going to set the wind-driven flow to 0 because it really isn't too much cross ventilation. And I'm going to set the discharge coefficient to be for insect screens, which is 0.17 you see there if I hover over that. All right. So we've got some natural ventilation. We've got our zone. Now let's go ahead and simulate this. And in order to do that, I'm going to grab the Open Studio component, which you remember I had explained that's the interface for Energy Plus that we're using. And this component here is going to take our zones as input. I'm just going to connect those up there, and it's going to export them run them through the energy simulation for us. Let's see, for our, we need a weather file, so in order to do that, I'm just going to go to EPW map, which hopefully many of you are familiar with right now. There's a component that will actually take you to this, but you can just search EPW map, and that'll take you here. It's just a map that Mustafa, the creator of Ladybug, has made for all the weather files across the planet, and I'm going to look at Syracuse, New York. How is Syracuse? Okay. Yeah, because I'm going to imagine that this is in upstate New York, kind of close to where my brother is living in Syracuse, we said. But you guys can feel free to pick any climate. I mean, you're going to get the most mileage out of this if it's a colder climate. But in any case, all right, so I copied that URL. We're going to bring that URL into here. Again, this is a lot of review. We're going to bring that weather file URL, connect that up to here. That's going to unzip the weather file, download it, and zip it into our system, our EPW file. I'll connect that up there. And finally, we're almost at the end of this. We just need to check add some simulation outputs. So in this case, I'm going to add in, let's see, I'm going to use the generate EP output component, which is under the 10 tab here. And I'm only going to ask for just comfort metrics, because there is no energy use really, because we haven't put in a heating and cooling system. At least there's no thermal energy use. So I'm just going to connect the true Boolean to comfort map variables. No, sorry, not comfort map variables. I want to comfort metrics. That's what I want. That's going to give me temperature, operative temperature. That's going to give me a sensation of what it feels like in the space. And I'll connect those simulation outputs there. And finally, there's one other thing I'm going to do, because we're really only interested in running this, just in the cold part of the year. So I'm going to be a bit ambitious. I'm going to say that I want to be able to occupy this treehouse in March, in New York, March, and there's snow on the ground, and I want to be able to occupy it without any heating system, kind of. So we're going to set our goals very high at first. So I'm going to just drag and drop a Ladybug analysis period in order to set that time period. And I'm going to double-click quotation marks, enter for 3, in order just to say that it's in March. So that's going to be our from month and our to month. And you see this is going to spit out a small little, whoops, if I bring up a panel here, a small little tuple that just says, okay, just run it for the month of March from March 1st to March 31st. And I'll connect up that analysis period there. All right, and let's see what we get. I'm going to set up a Boolean toggle to write the OpenStudio model, and then another one to run the simulation. And if you have OpenStudio installed, you see it'll run the simulation. It's going to be really quick because it's a zone, just one zone, and it's only for 1 month. And now we're going to bring those results into Grasshopper here. So I'm going to drag and drop the Honeybee read EP result component on the canvas and connect up the result file address from the OpenStudio component. And finally, here we are actually able to see what is it like inside our building in March. And I'm going to connect up the operative temperature here, which is that average of the air temperature and radiant temperature. And we see, ooh, it is chilly in this place, 5 degrees centigrade. All right, it looks like it gets up into almost a comfortable range. It's almost getting to 18. But oh, that's not good there. It's getting negative. Ideally, we really want to look at this graph for the whole time period, not just the stream of numbers. So I'm going to drag and drop the Ladybug under the Ladybug tab, Ladybug 3D chart, and I'm going to connect up the operative temperature here so that you guys can see it. And I'm going to go over to the top view. And so now we can see, all right, the temperature, wow, it does get up to something pretty warm. It gets up to 27 Celsius, just with these kind of normal standard average U.S. default constructions. But I mean, look at this. Wow, it goes down to -6. That is definitely not. I mean, any water that I have in this space is going to freeze. This is not really going to be occupiable in March the way it is right now. And I'm just going to do just a few graphic details just to make this a little bit more clear. I'm going to set the z-scale to 0 so that we can kind of read. You guys can read it over the course of the day there. What else? And I'm just going to move this kind of away from the, from our zone here. So I'm going to set a base point of 100, 0, 0. These are just Rhino coordinates. All right, so this is not really occupiable right now. So let's now introduce our therm construction into this. Now that we've kind of built a rough energy model. And so you guys remember last time I actually have the results here. I'm going to show the results, show everything again. Oops, show. All right. And you guys may remember, so we looked at 3 different constructions, wall constructions for this thing. We looked at that steel stud, which you guys remember was not so good. We looked at a wood stud, and we looked at a structural insulated panel, a SIP. And so I actually have baked the results here into Rhino for you. And if I turn off the polygons here, you guys remember the steel stud, it almost doubled the heat flow, doubled the U value. Actually, that's almost more than doubling it. And so we said we're definitely not going to do that one. In the same way that my office never does this type of construction anymore because we get so much heat flow through the steel. And then if we looked at like no thermal bridges, which is the structural insulated panel versus the stud, the two were actually pretty close. That using wood was pretty close to actually having no thermal bridges at all, basically. And so I'm going to say for our intents and purposes that, you know what, in this case the wood stud was good enough. Even though we could get better by going to a SIP, I kind of like the wood stud because it allows me to, use like some type of cellulose insulation or something as maybe a lower embodied energy than the foam that a structural insulated panel would need. And I say that's, I think this, this is a decent U value probably, or at least one of the best that we're going to get for our kind of 8 inches of insulation. All right, so in order to do that now, let's take the results of this and try and work that into our energy model here, our full building energy model. And so first thing that we have to do is we have to kind of build up, because we want all the mass of this construction. The thermal mass of it matters a lot to the energy simulation because it's dynamic, precisely because it's dynamic, and because the thermal lag can actually end up affecting the results quite a lot. So we need to model these all as real materials, and by real I mean ones that have density, ones that have specific heat capacity and mass to them, and not just the way that Therm models them with only conductivity, only calculating R value or U value. So all right, in order to do this, I'm going to be working with a bunch of things in the 6 construction tab here. I'm going to drag and drop this energy plus construction component on the canvas, and this allows you to take a bunch of layers of materials and put them all together into a wall construction or any type of floor construction, anything for energy plus. And so I'm going to come up with a name for this at first. I'm going to double-click quotation mark and just type tree house wood stud. I don't know. You can name it anything that you want. But all right, we're going to connect that up to the name here. And you guys remember that there were about 5 layers in this whole construction. Let me see if I turn the polygons back on, and I'll turn the results off. So we had one layer kind of, I think I had said it was of gypsum on the inside. One layer, or it could be plywood too. The two are relatively close. One layer of insulation, a layer of plywood or wood siding, an air gap, and then an outside layer. So that's 5 layers in total. So I'm going to bump this up to be 5 here. And I'm going to pull some materials from the construction library here. So I'm going to use this call from EP construction library. And you'll see I'm just going to use the EP materials for now because the EP materials have that mass. They have specific heat and density assigned to them, whereas the Therm materials do not. I would have to add those in basically. And so we have 1-inch gypsum right there. So I'm just going to right-click and copy data, and that'll automatically, the first one is what's going to be kind of copied into my clipboard. So if I hit quotation marks and then Control V, that'll just paste in that gypsum. So I'll hit Enter. And let's see, and I always forget, the order is layer 1 is the outermost, so layer 5 is the innermost, so that's going to be our gypsum there. Next thing, I'm going to leave layer 4, which is our insulation. I'm going to figure that one out last, because that's what we're really going to tweak to match our therm results. Let's see, so I'm going to model, I need some wood.